Yeah, here's a quick summary of what we learned in class about instantaneous velocity and acceleration. Up until now, we've done only either average velocity and average acceleration or uniform acceleration and constant velocity. And in those cases, it just takes simple algebra to tackle any of the situations we've come into. Um, But when we don't have constant velocity or constant uniform acceleration going on, calculus methods are needed to find certain values like velocity and acceleration in ways we haven't done yet. So generally speaking, in most problems we will be given something as a function of time. For this example, I'm just going to use position as a function of time. So this might be a given formula for something's motion and where it's at any time t. And if we were asked to find the instantaneous velocity at any time t, what we would do is find the first derivative using the power rule. In this case, is all we basically have to apply on a polynomial like this to find v of t. So another way we would say it is that v of t, a function for the instantaneous velocity, is the first derivative of the position time function. So applying your basic calculus rules using the power rule, the derivative of this term is just going to be 50. And the derivative of the next term, bringing the 2 down and multiplying it, will make this 0.6t. And doing that, we now simply have a formula for the instantaneous velocity at any given time t. Taking it one step further, we could find the instantaneous acceleration as well, taking the next derivative. So it is the first derivative of the velocity time function, or you could think of it as the second derivative of the position time function to find the instantaneous acceleration at any given time t. The derivative of a constant is 0, so that piece is gone. And in this particular case, the acceleration time function ends up being constant because the t goes away taking the derivative. So at any given time, this particular position time function gives me a uniform acceleration. That is not always the case, just for the example we've done here. Now we can go backwards, which we'll do later, because probably at this point in your calculus lives you haven't gotten to antiderivatives yet. But all that will do is show us how to go backwards. I could give you this function and go in any step possible backwards. But as you can see, in a simple case like this, it's just really basic power rule of the derivative, no fancy calculus that goes from one function to the next. Another important thing to realize is why what we just did right here works. Why does a derivative take me from a position time function to a velocity time function to an acceleration time function? And the answer to that is just simply, if you understand from your calculus class, what a derivative is. A derivative is finding the slope at any given point of a line. And if you notice, our first function I used in the example is actually quadratic. That means if we graph this function, x of t, we can get some kind of parabola looking thing like this. And we obviously can't use basic algebra to figure out the slope of this graph, as we learned before. If this was linear, we don't need to do this. We could find slope if this was linear using basic algebra, change in y over change in x. But the problem is, on something that is curving, slope is changing at any given moment. So we need to use a derivative to find out the equation for the slope at any given moment, which is what v of t is. Now it turns out in this example, if we would graph this function here, we actually do get a linear line, which means it's not totally necessary to use calc to get to the a of t function, because the v of t function that comes out linear, because this is basically y equals mx plus b form, we could actually apply basic algebra, change in y over change in x, to figure out this value. However, that's not always the case. There might be many situations where we take this derivative, get to the v of t function, and get a nonlinear equation, which then would bring me to an acceleration that still has a t involved. So maybe it's not completely necessary to do it this way, but the point is you can still take a derivative even though it is still linear, and really it's probably easier to do that with the givens like this in the form of the equations as functions of time.